Hello, and thank you for watching my presentation. Echolocating bats rely on an innate time reference. My name is Eran. I'm a postdoc at Dartmouth College, and this work was done together with Yossi Yovel during my PhD at Tel Aviv University. Bats measure distance using the time that passes between an echolocation call production and its returning echo. This is encoded by delay-tuned neurons that fire only for specific pulse echo delays with different neuron populations corresponding to different delays. With reference to the speed of sound, the distance can now be calculated. These neurons exist in bats' brains before birth, but unlike what we tend to think, speed of sound is not constant. It's affected by temperature, by humidity, by altitude, so long-lived, highly mobile animals such as bats can experience quite a range of speeds of sound. For example, Kuhl's pipistrelle, a common bat species that we used in this study, can experience foraging temperatures of 5 degrees Celsius at dawn in winter in the Israeli desert highlands right here, while only 150 km to the south, it may experience 40 degrees at dusk in summer. That translates into more than 6% shift in speed of sound, and you can think about high-flying bats that can experience significant shifts as well. So there is a potential advantage in either plasticity or a learned component in coupling these pulse echo delays to distance in the real world. We thus hypothesized that if we raised pups in altered speed of sound environment, they will show sensory adjustment, and if we expose adults to altered speed of sound for extended periods, they will show some sort of sensory compensation. We tested this by keeping bats in a flight chamber where they were trained to land on a target, right here, and in which we could increase the speed of sound by enriching the air with helium, creating a helix medium that transmits sound quicker, and so the returning echoes from the target would make the target appear closer, as you can see right here. Adults were exposed to periods of days to weeks, pups were raised in either helix or air since birth, and we measured the bat's range perception by using echolocation parameters that we validated in a previous study as good indicators of this, which are the duration of pulses in the last pulse strobe produced on the wall before takeoff. So the duration of these calls over here, this group of calls, and the interstrobe interval, or ISI, which is the interval between this last strobe on the wall and the next strobe that includes the takeoff itself. So this interval right here between this group of calls and this group of calls. Our hypothesis was not supported by the results. If bats adjusted their sensing, we would expect to see no difference between normal or increased speed of sound in pre-takeoff parameters, but this is not what we see. The ISI of pups was longer in air than it was in increased speed of sound, and that was correct both for pups that were raised in air and for pups that were raised in helix. Same story holds for the adults. So the values for air are higher than increased speed of sound. And interestingly, when we look at values of increased speed of sound for a far target, we see that they don't significantly differ from the values of air for a closer target. So that tells us that the bats have always perceived the target in speed of sound increased to be closer than it actually was. In flight, the story is similar. When bats approach a target, they shorten their call durations and intervals according to the distance to the target. They change their body position in preparation for landing, and when they perform this task in helix, they begin all these changes way too early. When we look at the interpulse intervals during flight in an adult, in a pup raised in air and in a pup raised in helix, and compare the values between flights in air, blue, or in helix, green, where there are solid circles for hits or empty circles for misses, we see that as the bat nears the target, so the target is here and this is the distance to the target, the values decrease, but in helix they begin at much lower values than they would in air. We also see that as the bat nears the target, the error becomes smaller. That is because 15% of 30 centimeters is an absolute error, which is less than 15% of 130 centimeters. So to sum up, no sensory adjustment to new speed of sound, suggesting no neuronal plasticity, and the time reference is innate. So why would a trait that theoretically benefits from plasticity evolve to be fixed? We think it has to do with the ecological constraint of a short period for independence and the necessity for functioning echolocation early on. If the bat needs to echolocate properly in less time than it would take to learn, then it is advantageous to simply be born with it, especially if the cost is not too high. So with this, I'll end. Thank you very much for listening. Please pause the video here to see who helped this project. Also find my contact info for any questions, especially if you're not staying for the Q&A. Thank you again for listening and enjoy the rest of the conference.